We have to generate energy. What is the best way to do this from the point of view of, making sure that it's there for the next generation, making sure that we don't waste land that we should be growing crops on to feed our people. We know what we're doing. We know it's safe now. We know it will be safe in the future. And I don't think there is much question about that when it comes to nuclear power.
The Rational View is a weekly series hosted by me, Dr. Alan Scott, providing a rational, evidence-based perspective addressing important societal issues.
Hello and welcome to The Rational View. I'm your host, Dr. Al Scott. On this episode, I'm going to be continuing my series on nuclear power. This episode, I'm going to be interviewing a medical expert who has expertise in looking at the impacts of radiation on cancer. And we're going to try to tie this in with the Fukushima perspective that we're getting now 10 years on after the Fukushima Daiichi accident triggered by the tsunami and earthquake. So I'm really looking forward to this interview. Got a great interviewee. So stay tuned. And if you enjoy this content, please hit like and share with your friends. Dr. Gerry Thomas is Professor of Molecular Pathology at Imperial College London, and until 2016 was Clinical Director of the newly established West London NHS Genomic Medicine Centre. She's a serial biobanker, having established the Chernobyl Tissue Bank in 1998. She was the scientific director of the Wales Cancer Bank and was project director for the Imperial College Healthcare Tissue Bank. She was awarded an OBE in 2019 for services to science and public health. Her scientific research has been focused on thyroid cancer. She has carried out research into the health effects of the Chernobyl accident since 1992. Gerry has published extensively on the molecular pathology of thyroid cancer and is an author of a number of reviews of the health effects of radiation exposure following nuclear accidents, having contributed to IAEA publications on the Fukushima accident, UNSCEAR publications on the Chernobyl accident, and more recently an IARC review of thyroid monitoring after nuclear accidents. Professor Thomas, welcome to The Rational View.
Hi.
I am honored to have an author of the infamous UNSCEAR reports on Chernobyl on the show. I've referred to these reports many times in my discussions on the internet and on my podcasts, and I've been called a shill for the nuclear industry for suggesting that fewer than 100 people were killed by the Chernobyl accident.
I'm afraid that happens to all of us.
I've been told that the UNSCEAR report is a government-funded cover-up. Can you tell me a little bit about that process, about your co-authors? Were you under pressure to cover up radiation effects on the populace?
Absolutely not. I mean, these reports take many, many years to actually put together because basically you have a bunch of scientists reviewing extensively all the publications that have been published and agreeing on a form of words for the report, which then goes to editors, and it's quite a long process doing this. And I can assure you, they are scientists; they are not in the pay of the nuclear industry at all. I know it's an easy thing to say, but there is no suggestion at all that any of us are other than independent scientists.
Interesting. So, I thought I'd ask you to discuss with us the medical impacts of radiation, and maybe in light of the 10th anniversary of the Fukushima Daiichi meltdowns, to help give my listeners some perspective on the risks of nuclear accidents. So maybe as a starting point, could you provide maybe an overview for our listeners about the health effects of ionizing radiation?
Yeah, I mean, people think that ionizing radiation is something that only comes from a man-made operation, but actually that's not true. If you live on this earth, you are surrounded by ionizing radiation. You can't avoid it. There are isotopes that are present in the food that we eat, in the water that we drink, and also in the air that we breathe, because if you live in an area where there's a large amount of granite, for example, you get a lot of radon gas, which seeps up from the ground. So you just cannot avoid radiation if you live on this planet. People, are under the impression that things like uranium are something that only comes from the nuclear power industry or from nuclear bombs. But actually, uranium is present in seawater. So every time you go for a swim in the sea, you're exposing yourself to uranium. Small amounts, but it's still there. And I think this is part of the issue that we have, is people think that exposure, no matter what the dose, is what causes the problem. But actually, we know from every toxin that we're exposed to, that there is a dose response curve for every single toxin. And for radiation, it's believed to be a straight line. There are arguments over whether it really is a straight line, or whether there is a threshold above which we only see reactions and health effects. But it's no different from any other toxin to which we're exposed. And actually, we know an awful lot more about radiation than we do some of the chemical toxins, for example. And it's very simple. If it's very low dose, then there's going to be very little effect on your health. And unfortunately, people think that if there's a nuclear accident, like in Chernobyl or Fukushima, then it's very high dosage levels to the population. And that's just not true.
Really?
To the people around, actually in the plants, and Chernobyl in particular, there were high dose levels. But to people who were living in the surrounding areas, no, those were very, very low doses. And unfortunately, I think we've conflated nuclear weaponry with nuclear power, and seem to think we will see exactly the same thing. And of course, they're totally different processes. The physics is the same, but the way the engineering goes around the two processes produces very different results.
Interesting. So the UNSCEAR report on Fukushima suggests that negligible excess deaths are going to occur as a result of the accident.
Yeah.
I've also looked around on the media, and groups like Union of Concerned Scientists says thousands of people will die because of Fukushima, and they're using this linear no threshold thing to project out the effects of tiny doses on billions of people.
Yeah, I think the best way I can explain that is to pinch an analogy from a friend of mine. And it's a bit like if you're a man, when you shave, you might cut yourself and you might lose a little bit of blood. Now, that won't have any effect to you as an individual. You'll blot it off and you'll go off and you'll do whatever you're going to do for the rest of the day. But if you add up all those small droplets of blood over a very large number of men in the population, you'll end up with a substantial volume of blood. And it's like saying, if you lose that amount of blood, then all of those people are going to have lost individually that amount of blood and suffer the health effects, which just isn't true. So if you can imagine, if one man loses 1 ml of blood, and 100 men will then lose 1 liter of blood, and of course, if you lose more than 2 liters of blood, then you might have a significant impact on health. And you can see how those figures build up. But that isn't the reality, I'm afraid. If you're exposed to a low dose of something, it's very unlikely for you, the individual, to suffer any consequence at all.
Indeed. And I think it's the statistics of these low likelihoods and large numbers that they're trying to play on to.
Yeah. I mean, we're not very good at looking at statistics and percentages and things like that. So it's easy to make those numbers scary. But in actual fact, I'll give you another example. And it's one that I use a lot on my slides when I talk about this. If you give 100 Americans 100 millisieverts each, okay, so that's quite a large dose. That's about 10 times the dose that most people got from Chernobyl, from something like cesium, for example. And that's in the areas that were contaminated. But if you have 100 Americans and you give them 100 millisieverts each, then only one of those would be likely to develop a radiation-induced cancer, and 42 others would develop cancer from other causes. So as somebody who's interested in cancer, I'm much more concerned about what causes the other 42 than what might cause the only one that might be caused by that. And of course, as it's a linear dose response, as you drop that dose, you drop those numbers. So to get, say you had 10 millisieverts to each person, we'd have to expose 1,000 Americans to 10 millisieverts each to stand even a chance of finding one cancer that was caused by the radiation. And 420 out of 1,000 people will get cancer from other causes. So as far as I'm concerned, that level of radiation is really minuscule in terms of public health.
Now, I like that perspective. I'm always trying to put these things in perspective for my listeners and to give them an idea. And science has really only been able to measure increases in cancer down to about 50 or 100 millisieverts, which is a huge dose relative to what you typically get in the environment, which is like 2 or 3 millisieverts in a year from the natural background uranium and cosmic rays and all the things that are affecting you. And I've seen it looking at the actuarial tables. 50 to 100 millisievert dose is roughly equivalent to drinking 1 bottle of wine per week, or 5 cigarettes per week.
Yeah, I mean, cigarette smoking is really not very good for you at all. And there is actually radiation in cigarette smoke. There's polonium-210, which actually you'd be quite surprised at the dose that you get if you smoke 40 cigarettes a day, for example, over a year. That would be the equivalent of 10 millisieverts of radiation. So, it's one of those things that's very difficult to explain to people, because obviously not everybody drinks, not everybody's overweight. So everybody has their own sort of perspective of looking at these things as to what they feel is more dangerous than something else. But really, when you look at radiation, we know there are areas of the world, for example, where people are exposed to 50 millisieverts a year through just living in the environment they live in. And we know with those areas, there is no increase of cancer.
What?
So it would, yeah. I mean, there are places in the world where you go and sit in radioactive sands because it makes you feel better, because they're warm, obviously, because they're producing radiation. And they will soothe rheumatic joints and things like that. But people will voluntarily go and sit in those areas for a protracted period of time to make themselves feel better, because they think it's doing them good. But I think it's partly this whole idea of what's man-made and what's natural. So if it's natural radiation, then it's not going to harm you. But if it's something that's man has made, it's much more toxic, when actually the physics is exactly the same. But it's one of those peculiar things that we have in our minds, that anything that we do must be more dangerous than what nature can do. And being, originally a toxicologist and pharmacologist by training, I can tell you there's some very nasty natural toxins out there.
Yes, indeed. So as this is a rational view, I'm always searching for evidence-based data. And in terms of looking at the effects of radiation on cancer levels, most of this linear no threshold curve is based on the atomic bomb cohort study from Hiroshima and Japan, and following these people over their lifetimes and measuring the excess deaths due to cancer. So this is like an acute one-time exposure, effectively. Is there any good data on cancers from chronic long-term exposure to radiation?
Well, I mean, you look in the areas of the world where there is a higher than normal background radiation level, for example. That's a sort of area that you would do that, because you wouldn't voluntarily go and expose a group of people to protracted low-dose radiation. But if you look at those figures, you can see that there is no increase in cancer in those areas, which suggests that, and it isn't a stupid idea to think this, but if man has developed and evolved on an Earth that is radioactive, you would expect us, if we're still here, to have evolved mechanisms that protect us from that low dose level of radiation. And if you think of all the DNA repair mechanisms that are involved in our cells on a daily basis, not only for insults of radiation nature, but also chemical insults, you can see why we might have involved all of those different protection mechanisms. And we are an extremely long-lived species, really. Our cells undergo an awful lot of divisions. So we do need protective mechanisms to make sure that we read the code correctly when we divide our cells. So this all would make sense. And the best example I can give you is those local areas where there is higher than normal radiation. And if you want to go and look at a good review of this, I would recommend your listeners go and look at the radiation restatement by the Oxford Martin School. If you Google it, you'll find it. It's free to download. And it goes through all the evidence we have at low dose radiation and says where there is a scientific consensus, where there is no consensus, and where it's obvious that we have the right answer. So it's a really good read. It's designed to be read by the history graduate who's advising the minister, because most of our advisors in Parliament tend not to be scientists. So it's designed to be read by that. But there are several annexes that go into an awful lot more detail, and that gives you an awful lot of background of where our understanding of radiation has come from. It took 3 years to write, so you probably have some idea of how much information we had to wade through to be able to write that restatement.
That's very interesting. Thank you for that reference. I've been looking at the linear no threshold debate, which is pretty hot right now. There are people that are saying hormesis is actually the case, and that low doses of radiation actually trigger an adaptive response in the body to upregulate the DNA protection mechanisms. But radiation basically is the risk is that it breaks DNA strands and causes mutations, which can lead to oncogenesis, which is a term for cancerous mutations in the genome. And I was looking around to try to see, is there evidence for low dose rate increases in these mutations? And I stumbled across a paper, and I don't know if it's accepted or not. It's Vilenchik and Knudsen in PNAS 2003, and they're looking at cell. Basically, they're measuring strand breaks in cells in a petri dish. And they're saying that the natural frequency of DNA strand breaks is doubled with a dose of 1.5 grays, which is
that's quite a large amount of radiation, 1.5 grays. One of the things I would say, be very careful about taking in vitro results and applying it to an in vivo system. People who've been working on cancer for years and years and years used cell lines an awful lot. And then we realized actually they're not a really good model for looking at cancer in the human. So be very careful about that. And 1.5 grays is actually as much as that's the start of the level at which you might start to see an acute radiation syndrome if you gave that to an adult living person. Indeed. As a whole body dose. So 1.5 gray is a very large dose. We're not talking about doses like that. We're talking about milligray doses. So that to me is not an experiment that is in the real world when we're talking about the doses we're exposed to from things like Fukushima and Chernobyl, for example. Yeah, at least not for most of the population.
Trying to get a feel for the sort of relative effect of just normal toxins and just oxygen even. And and compare that to the radiation. I'm having difficulty finding.
Well, the answer is you really can't do the experiments, because you need to do it in vivo in man, because man is the model that we need to work with. And you can't actually do those experiments. It's impossible to do those experiments. And this argument about, what the shape is at the lower end of the level of dose, is it concave or a convex curve? Is it hormesis or not? To me, is actually quite a sterile argument, because the effects of those doses of radiation are minuscule in comparison with things like obesity, alcohol, smoking, stress. In terms of increasing your risk of cancer, low doses of radiation pale into its significance when it comes to looking at those things. So to me, I don't actually care what it looks like at the bottom end of the curve, because there are things that are much more powerful in driving cancer as a public health issue.
Yes.
That are nothing to do with radiation, and everything to do with actually lifestyle and how we abuse our bodies ourselves.
That's a very good point. The angle that I was looking at this at is trying to justify safety levels. And it seems like safety levels have been set using the linear no threshold as a worst case precautionary measure.
Yeah, you're right.
And in Japan, the safety levels are on the order of the natural background. So they're spending hundreds of billions of dollars equivalent to scrape the topsoil off of the surroundings of Fukushima and store them all in garbage bags. And this is a horrible thing for people driving around, gathering fear, seeing these mounds of earth stacked up. Are these safety levels reasonable? Is what Japan is doing reasonable and necessary?
I don't think it's strictly necessary. I mean, I have a lot of concerns about the decontamination that has gone on, and this obsession. I think it is partly a Japanese obsession with being clean. And so if something is contaminated, they need to clean it up. And that's a cultural issue as much as anything else. But the problem with skimming topsoil, of course, is that area of Japan is where they used to grow an awful lot of their rice. Fukushima rice was, the best rice in Japan. And of course, if you take away the topsoil, you actually damage all the agriculture as well. And that topsoil takes many, many years to replace. So you're also doing further damage to the economy. There's the psychological, viewpoint of this stuff is stuck there. It's really dangerous. It's being taken away from us. Therefore, we must be really scared of it. There's also the economic damage you then do, because you're actually making the ground for future generations much worse, because you've taken all the good topsoil away. So there's all of those issues. and I think this is where I have a real bugbear with regulators and things like that, is if you look at one risk and that is all you focus on, and you're not aware of other risks that you might be generating by your actions to minimize that one risk, you can actually make things an awful lot worse for people. And I think that is our problem with radiation. We are focused on this nightmare of it might give us cancer, and that is all we think about. We don't think about how our actions will affect other people around us, will affect future generations, and will affect the future economy. And all of those, as we've seen through the COVID pandemic, when your economy starts coming into problems and people start losing their jobs, there are mental pressures and all sorts of things. And that's exactly what we have seen in Japan. The disruption of society and community that went on through the evacuation has caused huge health problems. Nothing to do with the radiation. The radiation, and I've said this many times, the radiation did not kill anybody and it will not kill anybody. The problem is that our actions that we have taken, because we're so scared of the radiation, has actually killed an awful lot of people. About 1,700 people died as a result of a very hurried evacuation. Now, it's difficult to say that that should never have happened because this was not just a nuclear accident. There was also an earthquake and a tsunami to think about. So there may well have been other reasons why those people had to be evacuated. But I think it was done in a rush without proper medical support in some cases, simply because people were running away because they were scared of the radiation. Yet we know from good studies in Japan that if you actually did the same procedure, but with the appropriate support, people didn't die. So our emergency response to it, to run away, killed more people than the radiation ever would have done. And it's still causing people an awful lot of stress out there. A lot of people are still worried that they're going to suffer the consequences of being exposed to radiation, when we know now that the doses were so low that we're never going to see anything.
Indeed. So this is really interesting, and I think that the rational public policy aspect is important to me. And that's one of the reasons I do this podcast, is that public policy just isn't rational. We need to get the rational voices out there so that this doesn't keep happening.
Yeah.
So
well, funny enough, we actually published a paper. It was all written and sewn up and gone to the publishers before Fukushima happened. To mark the 25th anniversary of the Chernobyl accident, we published a big review in one of the clinical journals. And we'd said in the editorial there, the thing we did not learn from Chernobyl was how to communicate effectively the risk from radiation exposure. And then a month before that was actually due to hit the newsstands, Fukushima happened. And you just felt, oh God, we're going through all of this again. We're going to make all the same mistakes. And it was painful watching us make all the same mistakes again.
Yeah, the public reaction has been problematic, to say the least, in terms of governments shutting down their nuclear fleets and building up coal. And, the amount of deaths as a result of the changes in energy policy are staggering.
Yeah. I mean, again, it's the focus on that one single fear of radiation and looking at that risk only, and not being aware that if you open more coal plants, you're going to increase air pollution, which we know kills people. If and then you've got the issues of climate change. And I'm not one of these people who believes that everybody's going to die as a result of climate change, but there will be significant environmental changes which will impact on public health. So you have to consider all of these things. You shouldn't be considering one risk on its own. You should be taking, as we do in medicine, we take an idea of the risk in the round. I mean, nobody would offer themselves for an operation if you didn't believe that was going to be the best thing for you. But there are risks in having an operation. But we know the way operations are performed and the people who do them are appropriately skilled, and therefore we minimize all those risks. And we can do the same thing with nuclear power. In fact, nuclear power is the safest way to produce energy. But you wouldn't believe that if you Googled it.
No, there's a lot of fear out there. And I think you hit the nail on the head, is communicating the risk and communicating the benefit as well. I think there's been a general failure in the technical community to communicate to the public. And I'm not sure where the problem lies in the communication methods. But if you would look at the actions of the technical community in response to radiation risk, for example, to treat it as the worst thing in the world, to bury it underground, to treat it specially, to evacuate people. This gives rational people the idea that there's a cover-up. This radiation must be really bad because we have to do all these special things. And if it really was only like drinking a bottle of wine, why are they doing this? So rational people get this confusion.
I can totally understand that. And it wasn't really till I started working on this and started understanding the relationship between dose and effect that I got my own head around it. I was quite shocked when some of our nuclear engineering students at Imperial said that they don't like going to dinner parties, and when they get asked what they do, they're embarrassed. And I'm going, but hang on, you're going to provide power for the future for us. And they said, well, we don't know how to explain things. So we actually now sit down with them for an hour, a lecture a year, and go through all the health aspects. So they feel that they can defend themselves in a public place. And some of them actually go down the pub and pick arguments with people now, because they've now totally come around to the fact, well, if we don't talk about it, who's going to talk about it? And I think part of the issue we have is the industry's reticence to talk about it. And I understand that, because if you don't talk about it, nobody's going to criticize you. Then you're not going to have to defend yourself. And so it won't be in the public eye. So I can understand that but you can't do that forever. It's because we haven't talked about it. And it's because quite often, a lot of the time, it's the science takes so long to do, to get results that we're confident with, especially when you're looking at cancer studies after radiation exposure. We need 20, 30, 40 years worth of data. So somebody else can say whatever opinion they have in that 20, 30, 40 years, but you as a scientist can't come out and say, well, no, we do know the answer, because it takes 20 to 30 years to get there. So you're always on the back foot and always having to defend the science. Whereas I think now, with the results from the lifespan study in Japan that you quoted earlier, which actually, another thing that people misunderstand about that is they think it's all high dose. It's not. Nearly half of that cohort had less than 5 millisieverts, which is equivalent to 2 years living in Britain, for example, from the radiation dose. A lot of the population that survived the initial blast had quite low levels of exposure. So we've got that low dose study. We've got Chernobyl, which actually for most of the time is a low dose study, if you're looking at the population rather than the workers themselves. And we've had 35 years after Chernobyl, and we've had nearly 70 years after the Japan bombs. So we have massive amount of data now. So we should be looking at it and saying, actually, we got this wrong. This is not as dangerous as we think it is. And I think people are starting to do that. But it was only after Fukushima that I think the scientists woke up and said, we have to do something about this, because actually what's being reported in the media is not correct.
Yes. Even just this morning on CBC and Canadian radio, they were doing a retrospective of the Fukushima disaster, and the announcer said 20,000 people were killed by the meltdowns in Fukushima on national radio. It's like, no.
I was just listening to our BBC News, and there was a report by Rupert Wingfield-Hayes, who I know very well, and I've actually been around the Fukushima area with him. And a lovely report, talked mainly about the tsunami, but the introduction by the newscaster was, the tsunami and the earthquake and the nuclear accident or nuclear disaster. And they keep using the term disaster. I don't use the term disaster. It's an accident. We made it a disaster. But, it was, the inference was that there were, tens of thousands killed by the accident at Fukushima. No, the tsunami killed 20,000 people. And it does, I know Japan very well. I spent a lot of time in Japan. And it irks me that when you think of March the 11th, the first thing people think about is Fukushima, which didn't kill anybody, which will not kill anybody. And they forget about the 20,000 people who died as a result of the tsunami. And I just, I feel so sad, because that's the real tragedy.
Yes, indeed. Yeah, I find in the communications, and I've talked with a lot of people in the industry about what we should be doing. And some people say we shouldn't be talking about the risk. We should be talking about the benefits.
I agree. I think we don't talk about the benefits enough.
Because you have, radiation medicine, the isotopes that you get from the reactors for curing cancer. Radiation has cured more cancers than it's caused.
Absolutely. It's still the best treatment we have for cancer. And people forget that without the nuclear industry in its broadest sense, we would not have these radioactive tracers. We would not be able to treat people who have breast cancer, colon cancer, you name what cancer. Most cancers have some aspect of radiotherapy treatment to them. And many of those people would not have survived. But it's also, that you can use this for other things as well. If we want to talk about decarbonisation, we need to produce hydrogen.
Mm-hmm.
And wind and solar are not going to cut it when it comes to producing hydrogen, because you need vast amounts of energy to do that. Nuclear would.
Yeah.
And unless we start having these conversations, in 2 or 3 generations, they're going to look back at us and think, what was the matter with them? Why did they ditch something which could have really made such a difference?
It is really shooting yourself in the foot not to use nuclear and the abundant energy that you can get from such a small amount of material.
Absolutely.
The waste streams are so different. The orders of magnitude more waste from renewable energy than from nuclear. But people are worried about the nuclear waste.
And the other thing about the waste streams that come from things like solar panels is you've got toxic heavy metals in there. Now, toxic heavy metals are not going to degrade in the environment. At least radiation goes away. Okay, sometimes it may take a while, but it goes away. Once you have chemical contamination of land, it's really difficult to get rid of it because it doesn't naturally decay.
Mm-hmm, mm-hmm. So the fear seems to be the overriding concern. And by interviewing people like you and getting this message out there, I'm hoping that we can counter some of this and get it into the public eye. But there are a lot of people who just don't want to listen to it. It seems like if you talk to individual people and you can convince them of the data, the opposition to nuclear seems to be a mile wide and an inch deep. People just haven't thought about it, and the public discourse is against it.
Yeah, I agree. I think it is not something that people have talked about in the past. I think people are talking about it more now. And interestingly enough, I would not normally have gone and spoken to green groups and things like that. And because of Fukushima, I was actually asked to go and talk to some of the green groups to explain a lot of this.
Oh, very
and
good.
I was amazed by the response. I was expecting to have things thrown at me and called all the names under the sun. But I have to say, and the vast majority of times that I actually spoke to people, it was, well, we never knew that. And I think partly the science is quite inaccessible. I had to speed read the UNSCEAR report that came out a couple of days ago. And I was thinking, God, if I was somebody normal who doesn't have all the jargon in my head, this would take me days to get through because of the language that used. And I think that's part of the issue an awful lot of the time when we're looking at this. The language is inaccessible for the general public. There's a lack of understanding even at school level of basic physics and radiation. Some of that is because it's felt it's not safe to do the experiments that we used to do when we were kids to show us how easy it was to block alpha particles, for example. And so I think there's an awful lot that we've not talked about for years. And I think Chernobyl was probably one of the big reasons that we stopped talking about a lot of this. And we've got a hell of a lot of time to catch up. But if you actually go and talk to people and say, tell me what you don't understand, tell me what you find difficult, why do you think that way? And sit down and have a proper conversation with them. Often they'll turn around and say, well, then that doesn't square with everything else I know. There's something wrong here. Have I been misled? Mm-hmm. And a lot of the green groups now are starting to have factions within them who are actually pro-nuclear, which means that they are listening and they have realized, okay, nuclear is not perfect, but neither is anything else that we need to generate electricity. And actually, it's better than a lot of the other options. And so they are starting to support nuclear, whereas before they'd have just dismissed it straight out of hand. So, if anything good did come out of Fukushima, I think it was the fact that it gave a lot of us the ability to go and talk to people that we wouldn't normally speak to. And we had to find ways of communicating about it. So it did us an awful lot of good. And I think it's improved the dialogue around it, but there's still an awful lot more to do.
Yeah, there's a bit of an appeal to nature fallacy in the green groups.
Yeah.
That sunshine and wind are great, but the stuff you dig up out of the earth is not.
Yeah.
And one of them is renewable and the other isn't. But in terms of renewability, the amount of material you need to capture the sunshine and wind is orders of magnitude higher. So that isn't renewable. The infrastructure and the mining that needs to be done to get the same amount of power is immensely different in these two things. And the scale is just something that people don't grasp, I think.
Yeah, I mean, I've seen some very good graphics where they're trying to explain about the amount of land that is required to give you the same amount of energy. And if most of the UK would be obliterated by wind farms if you were to get anything like the energy we needed. Whereas a couple of nuclear plants around the coast give us, a large amount of the electricity that we need. And I think that's another misconception, that people don't realize that we actually need a lot of power, and it comes from nuclear in small amounts and small sites. Whereas if you try and replicate that in terms of solar and wind, if you can, because today we've got a gale outside, which will probably stop the wind farms going because it's too strong a wind. But most of the time we don't have an awful lot of wind, especially on land. And a couple of years back, we had about 3 months where we just had wall-to-wall sunshine, no wind whatsoever. Great for the solar panels on a house, but not really good for wind farms. So, we just don't have the land capacity to be able to generate the amount of energy that we really need, particularly if we're going to need to decarbonize other things by using hydrogen, for example. We've got to manufacture that somehow. And the last thing we want to do is go back to coal. And I come from the South Wales valleys. You don't need to tell me about the waste that came from coal. Those valleys used to be absolutely black when we were operating the coal fields. So, I know how bad the waste streams are from other things, but trying to convince people that we actually know far more about what we need to do with nuclear waste than with virtually anything else we manufacture. It's an uphill battle, and this idea that it's not safe to bury it underground when we actually know it really is, because actually Earth had its own nuclear reactor in Gabon a while ago, and all its actinides stayed where they were. They have not moved around. So we know that putting things under the ground is probably the safest way to go. Indeed. Whether we really need to do that, again, I think there's some discussion to be had around that. I would like us to see us retrieving a lot of the used fuel and things that we can do. But, a few years ago, we just chucked a plastic bottle away and didn't think about it. Now we recycle that. So I think in the future, we will be recycling an awful lot more as well.
Wow, yeah. So you've basically just devastated all of the anti-nuclear arguments. You've addressed the health risks of Chernobyl and Fukushima, and the waste risk, which are the three things that everyone brings up when you say nuclear is what we need.
Yeah. And but I still work with an awful lot of people who are not convinced by all of those arguments. So I don't think it's something that we're going to settle easily. I think we need a pragmatist approach. If we want a westernized lifestyle, we want energy to be able to run our hospitals effectively. And I always say to people, the last thing I want to do is have a kid that's had an accident, needs a CT scan. Oh, haven't got the energy to run the CT scanner because it's at night, so the solar panels aren't working, and it's very calm outside, so I've got no wind energy. I have to have something that will operate that machinery. And we can't go back to living how we used to with a log fire and no electricity. And people don't want to do that. And if you suggest to a bunch of teenagers, could you manage without the internet? You see this horror written across their face. But the internet is powered by electricity. Where do you think that comes from? So I think, we have to generate energy. What is the best way to do this from the point of view of making sure that it's there for the next generation, making sure that we don't waste land that we should be growing crops on to feed our people, building solar farms or wind farms or whatever, and making sure that we know what we're doing. We know it's safe now. We know it will be safe in the future. And I don't think there is much question about that when it comes to nuclear power. I think there are still questions about waste materials from some of the other forms of power that we really have not addressed quite as well.
Indeed. I think nuclear has been held up to a very bright light for a very long time. And, you see every wart on it, whereas no one is looking at the options. They're just jumping into them without looking. And I think that's where the error lies in public policy.
Yeah.
The feedback from someone who's actually working on the medical aspects of this and understands the radiation interactions, because I'm coming from a physics background, I don't really know, is this right? And I'm constantly questioning myself.
Don't worry, you're not the only one. I think that's the mark of a good scientist. somebody who's always questioning themselves, saying, have I got the right evidence? Do I know where this comes from? Is it a good paper? That's the mark of a good scientist. So, and it is difficult. I mean, there seems to be this sort of divergence in the human brain. You either do biology or you do physics, and you very rarely get people who can actually understand both subjects particularly well. I mean, I make no bones about it. I was useless at physics at school, and I've had to learn an awful lot more physics as I've gone through my life. And I'm fascinated by it now. I just don't have the mathematical brain that would have ever enabled me to do physics as a career. But I think we do need to have more of a meeting of minds. And I think we need to recognize that a lot of the talks we have to have are multidisciplinary. And we also have to understand psychology as well. Scientists get on very well with each other, and we understand each other, we get where we're coming from. But when you take us out of the lab and put us in front of the public, it becomes an awful lot more difficult. And I think we also probably need to work with social scientists as well, so we can understand how we communicate an awful lot better. So I think there are a lot of challenges out there. And if there's any young scientists listening, public communication is going to become more important as you go through your research careers. So make sure that you understand how to do this and you get some help on how to do it. Don't stay in your lab. Science is no good to anybody. It's no good to mankind if it stays in a lab. It has to be used by society.
That's a very powerful message and well taken. It's unfortunate that most of the messages from our generation are cautionary ones.
Yeah. That's regulation for you. I mean, you do have to be cautious with things. You have to be aware of the risks, but you should never blow the risks out of all proportion. And I think that is exactly what we have done with nuclear power.
Yeah, it's definitely a dichotomy when you start understanding the actual magnitude of the risks and you look at the licensing requirements that are slowing down the build of new nuclear plants compared to what you need to build a coal plant, which definitely kills people when it's operating properly.
Yeah, I know it is
mind.
frustrating. It's very frustrating because you think that these things could really make a huge difference. I mean, we're lucky we're starting to rebuild in the UK. And I've actually been past the Hinkley Point sites, and you can view it from all over the Quantocks. I mean, it's a superb engineering project, never mind anything else. And you think, well, I know people say it's a blot on the landscape and all the rest of it, but it will produce so much power from such a small area. Surely that has to be worth it.
Indeed. Well, I'd like to thank you again for joining me on The Rational View and helping to spread your expertise to the world. It's definitely needed, and I had a great time speaking with you about this. Thank you so much.
Pleasure. Thank you very much indeed. Thank you.
If you'd like to follow up with more in-depth discussions, please come find us on Facebook at The Rational View and join our discussion group. If you like what you're hearing, please consider visiting my Patreon page at patron.podbean.com/TheRationalView. Thanks for listening.